Okay, and welcome back to the general track. We're going to be resuming with the second talk of the afternoon session, and we'll be hearing about reproducible science made easy, package management with Pixi from Wolf and Ruben. So without any further ado, please take it away.
Hello everyone, we're excited to be on stage for this talk. I'm Wolf and that's Ruben. I hope you have already met us out there with the puzzle. The first thing that we want to do is actually start with a demo just to give you a general look and feel of what Pixi can do. And the way I usually do these demos is I start with Pixi Global. So Pixi has two modes. One is the global installation mode and one is the project-based installation mode. And so you can use Pixi to globally install, for example, BAT, which is a tool to, it's cat with wings. So globally installing means I install this tool globally. I don't need administration rights. So even if you're on a lockdown Windows, you can use Pixi to install some of the CLI tools that you might want. And now I can just use BAT to, for example, look at this file. And this file is the Pixi TOML file. And in that Pixi TOML, I can define my project dependencies and my tasks. And I can use that to run start. So in this case, I have IPython, IPyWidgets, JupyterLab, bunch of stuff. And we can just do Pixi run start. And Pixi will take care of everything at this point. So it will install all the dependencies. It will create the log file. And it will start up JupyterLab without having to do any like activation or things like this. It's fully automated and just starts up JupyterLab. And you can immediately start using it. Whoops. And the thing that I wanted to mention is the Pixi log file, which locks down all the packages that are part of the environment precisely. So if you check this into your Git repository and hand it over to your coworker, they will get exactly the same environment. And that's one of the cornerstones of the reproducibility that we want to talk about in our talk. And now I'll hand over to Ruben to walk over what Pixi is and how we're doing things.
Yeah, thank you, Wolf, for the introduction, but I will go a little bit deeper into who we are. So, as said, we are Wolf and Ruben, but Wolf was the creator of Mamba. He's the starter of this company, already been doing package management for 5 years, and I'm Ruben. I'm working in robotics before I did package management. I really felt that this problem needs to be solved, so that's why I'm here with Prefix to really work on this. But we're not alone. We're a nice, small startup still, but have a great team that all works on this problem, so kudos to them as well for working on this. So this talk is also a little bit about Python itself as a glue language. So we are doing more than just Python with the Conda ecosystem and Pixi in particular. So we want to just mention that like Python is not built in Python. Python is built in other languages, just like C++, Fortran, CUDA, and Rust. And we're going to show you later on why that actually matters and how we're trying to make that a lot easier. So you guys have probably all seen some of these errors before where some kind of include didn't work. And what do you mean include? I'm always importing in Python. But the problem is that you probably need some kind of build systems and build tools to get your setup ready for actually using some of these Python packages. And this can be pretty complex, especially the first time that you're trying to do this. You're probably learning about Conda or any other package manager that you're familiar with, like Brew or opt, to get it figured out and make sure that you can actually run your Python packages. And it's pretty difficult to ensure the compatibility between these libraries and the Python versions that you're using. So having that all automated can be pretty cool. But so I've been talking about this problem. What is actually the solution? So in our opinion, the solution is the Conda ecosystem. So Conda ecosystem is a cross-platform language-agnostic package manager, meaning that you can run this on both Windows, Mac, and Linux, and for any language. So all the previously mentioned languages are all supported through this ecosystem. And then it's already been a pretty large ecosystem for a long time. We just seen in the tools plenary that conda-forge has been existing for over 10 years now. So there's a lot of packages actually already available through this ecosystem. Next to that, it's pretty easy to make these packages. It is actually getting easier because of some of the tools that we're also working on. But the idea is that you create a recipe to create a package, and then you can help others use these packages fairly easily. We, as Prefix, are really modernizing this ecosystem. We believe that it has an insane amount of potential, but it just needs a little bit more energy into these tools. So that's what we're going to talk about more today. One of which is Pixi. Pixi is trying to really make this easy, as Wolf was already showing you. We want fast package management. We want the installations to be fast. We want workflows to be managed through Pixi itself, so you don't need extra tools to manage extra stuff. We want it to be very reproducible, so that lockfile is very important to us, so you can share your work with others and you can reproduce these environments without having to think about somebody updating something in the world that then suddenly breaks your workflow. And especially, we built everything in Rust, meaning we can share Pixi as a single binary. You can just copy it somewhere and directly use it. You don't have to install something to install Pixi. You can just copy the file in and you can be running. And last but not least, Pixi is using UV. More on that later, but that means that we both support Conda and PyPI in one tool. Sorry. I was saying fast, what does that actually mean? It's really hard to put it in a number, but I've tried some stuff, and yesterday I saw, PyTorch was actually pretty fast with Pixi to install. So if you do a warm install, meaning you already have a cache of the downloaded file, Pixi will install it in within a few seconds. Conda will install it also in a few seconds, but much more. So this is not really translatable into one number that shares it all, but just know if you're using Pixi, you're going to have speed improvement on all different levels, like downloading, like caching, like symlinking, like every part of package management we have worked on to improve. Then the workflows that you can create with Pixi are in our language called tasks, meaning, for instance, the first one is format, FMT, just run rough, alias, very simple, but you can go deeper. So you can also create a command that depends on something, meaning that you can create these graphs of tasks that you need to run. And these tasks can also have inputs and outputs. So if you want to make sure, just like what you're using make for these days, that your parts of your run are not run when you already have the created files, Pixi will also be able to have you specify that and make sure that everything from Pixi run start will just do the bare minimum to get you set up and running in one go. Then the log file that Wolf already showed here is a little bit more detail, or actually less detail, but making it more readable. It creates a file that specifies exactly what you have in these environments. And not just for the environment that you have locally on your machine, but all the environments that you want to support. So if you run your development environment locally, it might create only the packages for that, but Pixi will actually also check, what is the environment I want to run on production? What is the environment I want to run on CI? And all these environments are then locked into one file, and then Pixi can figure out which one to install when you need it. But reproducing your environments is already pre-checked, so Pixi will warn you if your environment will not start working on Windows while you actually ask it to do work on Windows. And so you can really avoid reproducibility issues up front. So I already said also single binary. I really don't think a package manager should need a package manager to be installed. This is what's made it really easy to share this work with everyone, and mostly it's just a curl command away to get Pixi running. And UV, we're doing Conda and PyPI in one go. We're not just using PyPI as an extra layer on top of conda-forge. We're actually seeing or looking at the Conda environment, taking note of which packages are already installed. For instance, NumPy is often installed through Conda, and then if your PyPI packages depend on NumPy, will not start overriding or clobbering your NumPy files with the PyPI versions to avoid these strange issues you might have experienced using pip and conda together. So we've been giving a similar talk like this before, and most questions were about, but what about UV? We really appreciate the work that the UV team is doing. We actually use UV within the code of Pixi, so you will not get not get UV installed when you install Pixi, but you will have the PyPI experience ready to use. And as you can see on the right, UV has the same ability as Pixi to use the PyProject toml. So if you want to support both types of workflows, you can simply do that by using the PyProject toml. See Pixi as an extension to also use the Conda ecosystem to make these projects a little bit more powerful. For instance, if you want to mix it with C++ and other languages. So this is actually the introduction to Pixi, but we have been working on another really cool feature that is slowly being rolled out, and we want to pitch you the idea of it today. And we internally call it Pixi Build. It's a little bit more than that, so here's a summary. It's the ability to create a full development workflow from source dependencies to fully built setups that you can deploy somewhere else. It also allows you to create monorepos, meaning you have one project that contains multiple different packages inside of it. You might have other teams making these packages, but they can be released separately and be built into one global environment, or not global, one project environment. And this really provides us with a lot of simplification over the fact that you don't really have to think about different build systems anymore. Everything can just be simplified down into a Pixi project, and then you use Pixi in the main repo to build your project. This also allows us to create some standardization in build types. So we can standardize how you create a C++ package. We can standardize how you create a Python package, which is already going great. But we can do this for all these ecosystems and then merging them together through Pixi to create one experience that you can share with all of your teams. And then you don't need any other tools anymore. So if you're used to Conda build or used to PyPI or whatever, Pixi can now do all of that in one go. I want to briefly mention what is behind the scenes of this. So next to Pixi, we've also been building Rattler Build. Rattler Build is really changing what Conda Build was doing, but with fully written in Rust, with a new recipe format, which is a lot safer and a lot faster. So on the right, you can see this graph of the black one being Rattler built, and the Conda one, the full line, is what it used to take to build these packages. And you can really see what type of time we're simply scraping off, not by speeding up the build itself, you still need to compile with C or something like that, but just by simply being faster at the package management side, we can really scrape these times down to a lot more manageable times in most of these cases. If you want to know more about this, feel free to go to rattler.build. Yes, I love this URL, to figure out more about what Rattler Build can do. So what is Pixi Build? One of the first features that it creates is the ability to create a package in your Pixi TOML. So next to the workflow that we just explained to create a workspace or a project, you can actually make a package. And for the package, you just define like what is the build backend that I'm using, similar to how you do that with Python build backends. And then you define which host dependencies and run dependencies you need to create this package. Pixi will then pick this up and be able to build this into a conda package. So then, if you create these packages, how do you use them in your bigger environments? So in your normal workspace environments, you can say, oh, I want Python from Git, if Python was having this Pixi package TOML, and SciPy from a path that you're locally developing on, and astral.sh from this recipe YAML that you copied from conda-forge. And you can still mix that with the normal conda-forge packages that you're used to. So this gives you really the ability to have this editable Python packages workflow, but for any language that you want to mix in, making it really powerful for cross-language platforms, cross-language packages. So some examples of how that could look if you have a monorepo is one big workspace with multiple packages in there, and they all have their own Pixi TOML. They don't need a lockfile anymore. The lockfile is overarching in the main workspace or the root of the workspace. And you can mix PyProject TOML and Pixi TOMLs together to create these workspaces and make it really easy to deploy these packages afterwards. Looking at time. So Pixi Build is then the last frontier in this story where, okay, you've set it up, you have a workspace, you have it running locally, you've been testing it. Now you want to also deploy this package and share it with the world. Pixi now can actually build these packages and now can actually also be able to upload these to the channels to share them with anyone to use. So they don't have to build them anymore. And this kind of really makes it one streamlined experience going from like development workflow to CI testing to then also deploying it into the Conda ecosystem, making it really easy to use for anyone to get started with your project and thus be able to send it to a channel. A little bit deeper into how that works. So the main power of these build setups is the build backends. So Pixi will just read a manifest and then figure out, okay, I need this build backend. From that point on, it kind of sends it off to one of these backends to do all the interesting parts on how to build that. But the main focus that we have is that it is standardized how to build something, that it's flexible because you can create these backends yourself, and that it's customizable because the configuration is just fairly simple and in your Pixi TOML or PyProject TOML, like you're used to with PyProject TOMLs for your Python wheels. And we're kind of creating the same experience, but then for any language. So what does happen when you call to these backends? Pixi will first ask it like, hey, backend, what can you say about this package? What can you give me as metadata? Which variants can I build for you? Which Python versions can I build against? Or which platforms can I build you for? That is all sent back to the Pixi solver, and it's gonna use the solve to figure out which packages it actually wants from these backends. And then later on, when the solve is done and you really want to install your package, you can ask the backend again, hey, can you give me exactly this package with this type of variant, and then the backend will build the package for you and it can be installed. This is all in one loop. You don't really have to care about this when you're using it, but it's basically the technology behind it, making it very similar to how the Python build backends work, except that we have this JSON RPC implementation, meaning that while we are using Rust on both sides right now, you can basically build this for anything that can use the JSON RPC interface to talk to these backends. So you can build them yourself, even going further than just recreating what we already did for some languages. And these backends are installed as packages. So Pixi uses the normal packaging workflow to get these packages on your machine, puts them in the cache, and then making it very fast to recreate these environments while developing on these packages. So I want to give the mic back to Wolf, because we have a little bit more demos to show you where this actually works.
Yay. So let's look at a few more demos. Let me start with the PyBind 11 PyBind 11 fireworks demo. Oh, this should have been gone. Yeah. So here we have one of these Pixi TOML files that is a workspace and also a package, which is kind of funny because now we can depend on ourselves as a dependency that we want to install into the workspace. And at the moment that we depend on ourselves, Pixi will look into the package section and then figure out how to build the package. And in this case, we're using the Python build backend that we installed from this channel, which is the Pixi build backends channel on prefix.dev. And we also use conda-forge as dependencies for just the build backend. And then we can configure that, and we can add additional dependencies. And what we already alluded to, Pixi makes it very easy to also use the C++ compiler or things like PyBind 11 and Python. And now, basically, the magic that we want to achieve is that this compilation is kind of completely hidden from you, except if you put -v in there. And our C++ project just works. It was all compiled. And this works on macOS. This should work on Linux and Windows as well. And the C++ code that was executed is all here. I could go in here and I could, for example, change the variants as well. Right now, I've decided to only compile for 3.11. If I put it to 3.12, it should recompile and build me the package for 3.12. So that is one of our demos. I can also show you a CMake package for which we would use a different build backend, which is the CMake build backend. This is a game. So if you, as a scientist, are bored sometimes, you can just clone this repository. It uses the Pixi build CMake backend, as I mentioned, and SDL2 as shared libraries. If I just run Pixi crispy do, Pixi run start. So it's always like we always use start as the default task to make it kind of easy. We get crispy doom built from source. And there you go. Can play this little game. The other thing that we wanted to show is if you actually want to do serious science, then you wouldn't want to do that locally on your little laptop, but you want to connect to a really powerful machine. In our case, we've used Brev to spin up we've used Bref to spin up a GPU-enabled machine. And on this machine, it's completely pristine. We can run curl to install Pixi with one line. Now we have Pixi installed. The next thing that we can do is we can clone our Git repository like this. And in the Git repository, we have two examples that use GPU. The first one is using Mojo to just do some, to just execute Mojo sierpinski.mojo file, which will draw us a very nice triangle. Now I can just run Pixi. Oh, now I did get it wrong because in this case it's Sierpinski, very hard to type. This is now running on a GPU. It was super easy for me as a developer to kind of recreate this environment that uses GPU and CUDA support. And the same goes for the other lava lamp example that we have here. That is a very intricate particle simulation. Again, this one is actually using, this works on Windows and Linux and needs CUDA. And it uses the CMake build backend. In the CMake list, we find the CUDA compiler, which we install with just this CUDA NVCC as a build dependency and then as a host dependency, so a shared library that we want to link against, and headers that we want to include is libqrundev. This is super smooth. I can just do pixi run start, and it will, like in this case, we can look at how it's compiling. So I'm adding this -v. So first we're going to solve, update the log file, and start compiling. So actually, the machine that we chose on Bref is like a little bit on the cheaper side, and it only has 4 cores. For the compilation, which takes a little bit more time. It has a very powerful GPU, so the lava lamp should work like a charm once it starts. But at least we demonstrate that it's actually compiling. And there you go. And again, like basically the magic is you can take that Pixi toml and your source code, share it with a colleague, and they don't have to know anything about like invoking CMake or figuring out what compiler version to download or what shared libraries are necessary or which sudo apt-get commands to run. It's just Pixi run start, and Pixi will take care of all of the compilation and all of the linking and whatnot, and just run it. And I think every one of us has experienced these long README files that explain you like how to apt-get install this, and then like brew install that on macOS and stuff like this. And so we really try to like make that super simple, single command, just use Pixi. And yeah, that was the extended demo. I think we have like 1 or 2 more slides. Yeah, so the outlook, like where do we want to take this next? We want to make it really easy to create custom build backends. So if we have like inspired by the posit table on the other side, we really want to have an R build backend, for example, or Meson, Fortran, all these kind of software we want to make very simple to build and install with Pixi. And we also want the community to do that themselves. We have been working really hard to also integrate recursive source dependencies, which means that you can depend on another build dependency also from source, and we will make sure that we build everything in the right order and link it into the workspace or link it into the build space, basically. And so we've chatted with a few other companies that are using Bazel for this purpose, and we want to build something that's like Bazel, as powerful as Bazel, but like kind of simpler to use, ideally. And then at Prefix, we're also working on many other Conda improvements, like signing with Sigstore for packages, optional and conditional dependencies for the Conda ecosystem, and all kinds of other things. We also quickly want to shout out that there's a Spider talk tomorrow at 2:35, and they've been working really hard to integrate Pixi into Spider, which is a really cool use case. So make sure to also check it out. You can try Pixi really easily. As I showed, it's a single line to install it. And that's it. Thanks for listening.
Okay, excellent. Thank you for the nice talk. So we have quite a few questions already, so let's see if we can get through these in a 5-minute speed round. But okay, going off of emoji response quantity first, we have a question from Jay. Jay says, I am an author of Python packages that publish to both PyPI and conda-forge. How do you see Pixi build changing the current workflow of publishing to conda-forge that has separate feedstock repos with conda recipes?
Yeah, so right now on conda-forge, there's only conda build and retla build supported and not Pixi to build the packages. At some point that might change. But in the meantime, what we also want to enable is that you basically take the Pixi project and you can generate a recipe from it, and then you could take that recipe and put that on conda-forge. So that would be kind of the stopgap solution. And then maybe at some point later, we will just have Pixi support straight away in conda-forge. And that will work like even more easily.
Okay. All right. And then we have a question from Peter. So does the UV code that exists inside of Pixi and a version of UV that you might install on your machine, do they share any sort of cache?
Maybe.
So they don't really. Pixi has its own cache that you can, that's completely disconnected from the UV cache currently. You can modify that, but right now it's not really recommended because the build stage of UV packages, if you use sdist, is not the same. So that might give you problems.
And then Gil asks, is it possible to use Pixi Global to install a command line interface tool from PyPI?
Right now, no. Pixi Global only supports conda packages, but you can install UV for that right now.
And then Keith asks to add on to Jay's question. Are there any plans or thoughts on building PyPI compliant wheels using Pixi build?
Yeah, that's kind of a dream of ours. So ideally, we'd also make it very easy to kind of build the wheel out of your Pixi project, especially for like more sort of like C, C++ dependencies. We could just take them from conda-forge or something like that, and then put them in the wheel. With some added magic. But that's an area that we haven't yet figured out. But yeah, hopefully we get to that.
Okay. And then Nodar asks, so Nix and PNPM, don't know that, make heavy use of symlinks for speed and space savings. He may be mistaken, but as he understands it, Pixi does copies of packages from the cache to the local.pixi folder in the project directory. So if that is correct, what is the motivation for this approach?
So that's luckily not true. Pixi prefers to use ref links, which are copy on write, which are actually the best kind of link. And if that doesn't exist, you fall back to hard links, which is basically different links that refer to exactly the same file. But the problem is if you change one in your .pixi folder, then it will also change in the cache. So that's why we prefer the reflink approach. Yeah, and in the worst case, like if you're on different file systems, then symlinks or hard links and all of these links are not really possible, and then we have to use copying. Indeed.
We should get stickers for the ref linking here.
Yeah. This is a question from me. So you covered this a bit when showing the Pixi manifest and Pixi build path options, but can you talk about how you see Python library developers using Pixi in their Python library work, where you might need to switch between your dev environment and some arbitrary user's reported environment? And what does the developer UX or workflow look like here?
Sure. So one of the ways that we would for example, NumPy developers, let's say, use this would be we can actually build Python from source pretty easily, which is what I was trying to demo here. And that would build, I think, Python 3.14. And so the idea would be like a NumPy developer could build the latest version of Python from source and link that into their own build space and build NumPy against the latest version of Python, for example. and that would make it easy to test against, Python and main or stuff like this.
Okay, I think there's lots of other questions, but I think we have time for one more quick one. So I'm going to choose Leo's. So Leo asks for example, when a wheel from PyPI when a Python package, wheel, and a conda package have the same content, how can Pixi avoid file corruption?
Yeah, so when we install PyPI packages, we first look at the conda environment to figure out which packages are installed. Then we link that back to a mapping that we automatically have generated, and then figure out which package it actually links to in the PyPI ecosystem. And only if that package is not already in the conda environment, we will start installing it. So we'll not really avoid that the files are being clobbered, but we're avoiding the actual full installation of that package. So you will not get into this situation.
Great. So there's continues to be more questions, which that's great. But so hopefully Ruben and Wolf can answer these in the Slack afterwards. But we're unfortunately out of time and need to have time for the passing period. So let's thank our speakers again.
Thank you.
You can also find us outside at the puzzle, and we're happy to talk more.